Welcome to the deep dive. You've brought the sources, the research, and the rough notes, and we're here to give you that expert shortcut, the essential high-value knowledge you need, delivered with precision and speed. Today, we're undertaking a really fundamental deep dive into covalent bonding.
That's right. And our mission today is all about foundational mastery. We aren't just looking for, a simple definition. We need to lock down the exact mechanism of covalent bonds and, this is the critical part, build a fence around this concept. We have to differentiate it perfectly from other types of bonding. By the time we finish, you will have complete fluency in the language of this essential chemical bond.
Fluency is definitely the goal. We've distilled all the material down to the exact points where most people, they stumble. So before we dive into all the complexity, let's establish an anchor point. If you could only have one sentence to capture the entire essence of this topic, what is the core idea we must take away immediately?
The anchor is this, and it's worth remembering. A covalent bond forms when two non-metal atoms share a pair of electrons, and this shared pair is attracted to both nuclei.
Okay, let's unpack that, because there are a few key elements right there that immediately they sort the entire periodic table for us. First, we are strictly looking at the interaction between non-metal atoms. That rules out metals entirely.
Entirely.
And second, the action is explicitly sharing, which is, it's fundamentally different from transferring.
Absolutely. And that identification of nonmetals is your, let's call it a chemical classification safety check. Nonmetals typically sit on the right side of the periodic table, and they tend to have high electronegativity. They really, really want electrons.
So when two of them meet, they both want to gain electrons to get that stable, full outer shell that everything's striving for.
Exactly. And if they both want to gain, neither one is willing to just, give up what they have.
So it's like a negotiation where neither side is going to transfer ownership, so they decide on a binding partnership instead.
Precisely. That partnership, that compromise, is the sharing of electrons. If we look at the process, step by step, the non-metal atoms approach each other, they realize neither can easily lose an electron, and they achieve that stable, complete outer shell, often called the noble gas configuration, by, pooling their resources. They share one or more pairs.
Okay, so sharing is the action, but what's the force? This is where the concept moves from a nice analogy to, a rigorous scientific definition. We need the physics behind the bond. Why does that shared pair actually hold the atoms together?
This is where we shift from just describing it to being really precise. We need the scientific vocabulary of mastery here. The shared pair of electrons creates this region of intense negative charge density right between the two atoms.
And the atoms themselves are mostly made of positively charged nuclei.
Exactly. So the precise definition is that the covalent bond is the electrostatic attraction between the shared pair of electrons and the positive nuclei of both atoms.
So the electrons are being pulled toward two positive centers at the same time.
Yes, and that powerful mutual attraction is the glue. It's what locks the atoms into position.
That makes the whole thing much clearer. It's not just sharing electrons, it's the resulting electrical force that holds the entire structure together. This really highlights why precision in language is so crucial here. The source material really emphasizes the absolute necessity of certain terms.
The language of precision is, I would say, non-negotiable. You have to use terms like shared pair of electrons, nonmetal atoms, electrostatic attraction, and nuclei. If you're explaining this concept in any serious context, whether it's material science, chemistry, engineering, that specific phrasing shows you understand the fundamental mechanism, not just a surface description.
And what are the critical trip hazards? The words that, if you use them, immediately tell an expert you're mixing up your chemical concepts.
Okay, number one, you must avoid saying that electrons are transferred.
Right.
And you have to avoid referring to ions attracting each other, transferring electrons, forming ions. That belongs to a completely different type of bond.
And I'm guessing vague language like the atoms stick together is just not going to cut it.
Not at all. It's insufficient. The focus must always, always remain on the attraction to the nuclei.
Fascinating. So we've established this strong, precisely defined bond. Now let's shift focus. When these strong bonds form, they don't all create the same resulting structures, do they? The source material draws a crucial distinction between two massively different outcomes.
They certainly do. And the outcome basically determines everything about the physical properties of the substance. Covalent bonding creates two major categories of structures. First, we have simple molecules. These are the small, discrete units you probably think of most often. HO, cocoa, euros, nitrogen gas, oxygen gas.
So individual separate units.
Yes, they're defined by having strong bonds within the molecule, but the molecule itself is, for the most part, isolated.
And the second type is pretty much the complete opposite of isolated and discrete.
That's the giant covalent structure. Sometimes it's called a giant molecular lattice or network covalent structure. This is where atoms are joined by strong covalent bonds in a massive continuous network that can, in theory, extend indefinitely. You don't have individual molecules. You have one gigantic structure.
And the classic examples being diamond and graphite.
Exactly. Those are the two best examples.
This presents an immediate and, I think, really interesting paradox, particularly with the simple molecules. If that individual covalent bond is so incredibly strong, rooted in that powerful electrostatic attraction, why do substances like water or dry ice have such low boiling and melting points? That seems counterintuitive.
It is the single most common point of confusion, and honestly, addressing it is the key to chemical mastery. You have to distinguish between the two types of forces at play.
Okay, walk us through that distinction.
The bonds inside the molecule, we call those the intramolecular covalent bonds, are incredibly strong. They require a huge amount of energy to break. But when we melt ice or boil water, we are not breaking the H2O molecule apart into hydrogen and oxygen atoms.
We're just separating the H2O molecules from each other.
Exactly. We are overcoming the forces between the individual HO molecules. And these are called intermolecular forces, or IMFs. For simple covalent molecules, these intermolecular forces are very, very weak.
So we only need a small amount of energy to push them apart.
A small amount of energy, which means low temperatures are needed to overcome those weak forces and change the state. The substance melts or boils easily.
That's the critical insight then. Low melting and boiling points are actually proof that you're dealing with weak intermolecular forces, even if the underlying covalent bond is incredibly strong.
Precisely. If you're ever asked to explain why methane is a gas at room temperature, the answer has to be about overcoming weak intermolecular forces, not the strength of the covalent bonds inside the methane molecule.
Right. Now let's pivot to the giant covalent structures, because their properties are so dramatically different. If simple molecules are soft, often gases or liquids. Giant structures are usually the materials we associate with extreme toughness.
Just think about diamond. It's one of the hardest known natural substances on Earth. This massive difference in property is entirely due to the structure. In diamond, every single carbon atom is covalently bonded to 4 other carbon atoms. It creates this massive three-dimensional tetrahedral network.
So it's all intramolecular bonds all the time. There's nothing weak holding it together.
Correct. To melt or boil diamond, you have to break millions upon millions of those incredibly strong covalent bonds. This requires an immense amount of energy, which is why diamond has an extraordinarily high melting point, somewhere around 3,550 degrees Celsius.
Wow.
It is also, because it has no delocalized electrons, an excellent electrical insulator.
And that leads us to graphite, which is just the most fascinating example because it's also pure carbon, but it's completely different. It's soft, it's slippery, it conducts electricity. What structural change causes such a dramatic shift in property?
The fundamental difference is the geometry. In graphite, each carbon atom is bonded to only 3 others, and they form these flat hexagonal layers.
Okay, so there's a 4th electron left over.
Exactly. That 4th valence electron is, well, it becomes a delocalized electron. It's free to move.
So you have these layers of carbon that are held together by strong covalent bonds, but the layers themselves are only weakly attracted to each other.
You nailed it. The forces between the layers are just weak intermolecular forces. This means the layers can easily slide over one another, which is why graphite is so soft and a great lubricant. It's perfect for pencils.
And the delocalized electrons.
Because of that one delocalized electron per atom, those electrons are free to move between the layers. That's what makes graphite a highly effective electrical conductor.
That structural contrast, the tetrahedral network in diamond versus the layered sheets with delocalized electrons in graphite, is a masterclass in how bonding determines physical reality. The entire structure changes, and suddenly you go from a crystal used in drilling to a substance used in batteries.
It connects the theory directly to application, and that is why we must have control of this vocabulary.
Okay, let's move to the 4th and I think maybe the most important control point. Creating that perfect intellectual fence between the two most common bond types. We need a final, clear, memorable distinction between covalent bonding and ionic bonding.
Right. If we connect this to the bigger picture, what we need to do is create 2 mental checklists. one for each path that you can run through instantly.
Okay, give us the checklist for the ionic path.
The ionic path begins with the transfer of electrons. That's keyword number one. It's typically from a metal to a non-metal. The result of that transfer is charged particles, which we call ions, a positive cation and a negative anion.
And the bond.
The final bond is the simple electrostatic attraction of those opposite charges. The goal is stability, but it's achieved through a complete electron transfer.
And now the covalent checklist we've just spent this time on.
The covalent path involves the sharing of electrons. That's the key verb. It's strictly between nonmetal atoms. The result is a shared pair of electrons, and the bond itself is the electrostatic attraction to the positive nuclei. The goal is stability through mutual sharing.
That clarity is just invaluable. It reinforces why using that phrase electrons are transferred instantly takes you off the Covalent map and puts you squarely on the ionic road. Misusing that single verb signals a fundamental conceptual error.
Mastery means you know the difference between those two actions. If you can define both bond types precisely, focusing on the action and the resulting force, you have complete control over this core area of chemistry.
Excellent. We've covered the definition, the precise mechanism, the resulting structures, both simple and giant, and that critical differentiation. To wrap up, let's just run through our self-check trio. The 3 facts that confirm you have locked down this knowledge. Self-check number 1. Covalent bonds form when nonmetals share electrons.
Self-check number 2. The ultimate force holding it together is that the shared pair is attracted to both nuclei.
And self-check number 3. The most precise definition is that the covalent bond is the electrostatic attraction between the shared electrons and the nuclei. If those 3 elements are second nature, you are ready to build on this knowledge.
And that leads us to the final thought we want you to explore on your own. Given the dramatic difference in properties we discussed between, say, simple molecules like water and giant structures like diamond, consider the implications for materials engineering. Why is it chemically, almost impossible to create a giant covalent structure that is also a liquid at room temperature? What structural requirements inherently prevent the existence of a high-strength, high-melting point network that is also fluid?
That is a fascinating constraint to grapple with. That's a deep dive wrapped up. We hope this precision in vocabulary and structure saves you time and elevates your understanding. We'll catch you on the next deep dive.